In this video, we will use Kruskal's algorithm to find minimum spanning trees. And in the previous video, I did a few examples and explained, well, why does Kruskal's algorithm make sense? In this one, we're just going to apply it without thinking about what we're doing. So here, we're returning to the very initial problem that I set up in the very first video, which was, let's assume that this is our town and none of these power lines are built. We're part of Problem Town, Gas and Electric, and we are going to try to construct power lines to make sure that all of the dots have power, and we're trying to spend the least amount of money in order to get that done. And now we know exactly how to solve it. We use Kruskal's algorithm. We want to find the minimum spanning tree. So here, we're going to start by highlighting the cheapest edge and continue highlighting the cheapest edge with the one condition that we're not allowed to make a circuit. So let's start with, it appears as though the cheapest edge in this graph was 1. So yeah, and notice that they're all numbered. Obviously, in a real problem, it wouldn't necessarily be quite so simple and sequential numbers, but just for the sake of practice. Next up is 2, the next cheapest edge, and so on. 3, 4, and basically we're just going to keep highlighting the cheapest edges. And another thing is, when you're working through this process, you might want to know, well, how do I know when to stop? But one thing that I recommend before really doing anything is always thinking about what's our goal? How many edges are we looking to find? And that's always n minus 1 by the tree property. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 edges. That means we're going to look for 9 edges. Our spanning tree must have 9. And it gives me a goal, right? As I'm highlighting, how do I know how many lines to highlight? Well, so far I have 4. I'm going to need 5 more still. And also one thing that, as we're building these, notice that the current configuration, none of these power lines are actually linked up together. But if I keep going through this procedure, they should all connect back together in the end. And so it does not matter that they're disjointed. I don't have to connect them in order like with the nearest neighbor algorithm. It's nothing like that. It's exactly synonymous to cheapest link, just with the differences that I talked about in the last video. Anyway, so I'm just going to keep highlighting the cheapest edges, 5, 6, and every time I'm making a selection, the only thing I need to pay attention to is, does this create a circuit? Because that's one thing I can't do, and so far none of those highlighted formulate any circuits. Next up would be 7. Also notice in this case, if we were trying to find a Hamilton circuit, this edge would not be allowed, because in the previous chapter, we were not allowed to use more than 2 highlighted edges. But here, it's totally fine, as I mentioned, because we are allowed to build more than 2 power lines from a particular vertex. There's no rule against that with spanning trees and with network problems. And I could keep going. 8, notice that does not make a circuit. But if I were to then use 9, the next cheapest link in the graph, notice that this one would not be allowed, because if I were to do that, that would create a circuit like that. And that's the one thing that's not allowed, circuits. So sometimes we will run into edges which are not allowed. And again, I would suggest putting an X to mark edges that we're skipping in the process. Last edge over here would be edge number 10. And actually, this would finish our problem. And how I do these problems is very visually. I'm going to keep connecting edges together until every single one is connected together. And basically, I can kind of tell that by tracing through and seeing, well, does each edge, have at least one edge connected into the network, right? Because at least one edge needs to be highlighted into each point. Sometimes there might be 2 or 3, like in some of these cases, but as long as everyone has at least one, I'm good. And I can also double check to make sure, did I only use this amount? Because I will not need more than 9 to do it. 1, 2, 3, 4, 5, 6, 7, 8, 9. Perfect. If I've used more than 9, there's got to be some redundancy in there. And just look for, well, there should not be any circuits. If you did use an extra edge, like say I did highlight this 9, we could figure out, well, which was the edge that I used that I shouldn't have, and how would I remove that redundancy? Well, I could look at this circuit and delete the most expensive edge, right? And that, kind of like I said before, there's so many different spanning trees that this graph could have. But we want to remove all the redundancy to make sure it is minimally connected. And anyways, this would be our optimal configuration. And often what you're going to be asked for with the homework is, what's the total cost or the total net weight, which would just be adding up all the numbers. So 1, 11, 14, 16, 24, 31, 36, 40, 46, I believe, assuming I did that uh, correctly in my head, um, which would be, and going back to the very original problem, we have now finally solved it. Um, and basically each of those were costing millions of dollars. So we can now, answer the question. It's going to cost us $46 million to build those power lines and make sure all of those cities are connected.